What if your network is letting through dangerous traffic right now? Standard ACLs can't protect you against modern threats, but extended ACLs can block attacks with surgical precision. In this lab, I'll show you how to create bulletproof security rules that stop hackers while keeping your critical services running. Watch as we configure, test, and verify real-world ACLs that actually work. In this practice lab, we will create an access list on router 1 with 4 rules. First, we want it to refuse all UDP traffic. The second will allow only TCP traffic from PC1 on port 23 for Telnet connections. The third prohibits all other TCP traffic from PC1, and the last will allow all types of traffic. The PCs and servers in this tutorial simulate iOS, not Windows. We'll start by connecting to router 1. And in global configuration mode, we'll create our access list, which we'll name test, with the command IP access list extended test. We want the first ACL to deny all UDP traffic, so we'll start by making a deny UDP any. The second ACL must authorize only TCP flows from PC1 on port 23, so we'll type permit TCP host 10.10.1.10 any EQ 23's errors. The third ACL prohibits all other TCP traffic from PC1. Type deny TCP host 10.10.1.10 any, and the last ACL will authorize all other traffic with the instruction permit IP any. Implicitly, there's always one last line in the access list that we don't see, a deny any rule, which refuses all traffic if no flow has been matched by the previous rules. To continue setting up our access list, all that remains is to declare it on the interface closest to PC1, that is, port 00. We connect to it with the interface command and send it an IP access group test in. If we return to privilege mode and run a show IP access lists test to check our configuration, the 4 rules we've just typed are clearly visible. However, we can't see the last rule, which rejects all other packets, but it's there by default. We're now going to test each line of our ACL. For the first line, as an NTP server uses the UDP protocol, we'll declare one on PC1 so that it connects to the server clock at the other end with the command NTP server 10.10.3.30. We can now check whether it has succeeded in hooking up to server 1 with the show NTP status command. We can see that the clock cannot be synchronized. Our first line of the ACL works correctly. The second line authorizes Telnet traffic for PC1, so we'll try to Telnet to the server at the other end from PC1 by launching a Telnet 10.10.330 WAN. We use admin for the username and Cisco 123 for the password. The second ACL matches well. The third is to refuse any other TCP traffic that hasn't yet matched. To test this rule, we'll try to make an SSH connection, again from PC1 to the server, with the command SSH admin 10.10.330. We can see that the connection doesn't open because the flows are blocked by router 1. And the last line authorizes any IP traffic not matched by the lines above. If we simply ping using the ICMP protocol from PC1 to the server, it should work and match our last ACL line. The ping goes through without a hitch. Our ACL rules focus only on traffic coming from PC1. If we run Telnet again, but this time from PC2, it shouldn't be a problem. And even SSH from PC2 to the server at the other end should work. PC1 cannot connect via SSH But PC2, on the other hand, has no restrictions, as it matches the fourth ACL, which is permit any. You can even ping PC2 to the server. To close this tutorial, we'll run a show IP access lists test. Here, we can see the count of our various tests. That's all for the ACL, and I'll see you soon in the rest of the program.